just for people who aren't tuning in. Hello, recording tuner inners. So chapter 5, 4, and 3, they're really all about taking derivatives, differentiation. And so we're taking functions like x squared, and the derivative of x squared is 2x. This is all stuff we know. Here's something interesting though, like the derivative of x squared plus 3, right, is also 2x, right? And let's see, later on before the break, we looked at the derivative of e to the x. Okay, that's e to the x, and derivative of ln x is 1 over x. And maybe I'll do like one more here, like maybe like e to the u. Its derivative is e to the u times u prime. So this is all old stuff. Chapter 6, really what we're doing is we're doing this like inverse mapping. So we're saying, given a derivative, what was the original function? And so for certain things, that's pretty easy, right? We know that e to the x came from e to the x, and 1 over x came from natural log x. But there's also this problem: if we just know that the derivative of a function is 2x, that actually doesn't give us the full picture of what the original function is. It could be more than one thing. It could be x squared plus 3, it could be x squared plus 1, x squared plus 1,000. And in fact, if we just know that the derivative of some function is e to the x, well, I mean, it could be that that came from e to the x plus 5, right? That would also be a function whose derivative is e to the x. So the first sort of like big picture idea that I think is helpful in this chapter is that when you take an antiderivative, you don't just get a single answer, you get a whole family of functions. So for example, if we know that the derivative is 2x, then the original function, right, if that's f prime of x, then the original function, it can't just be anything, right? F of x has to be x squared plus some number, and that number could be 0, right? It could be x squared plus 0, it could be x squared plus 1. And so the way that we sort of capture all of those things together is to write it as x squared plus c. And that represents now a whole collection of functions. They're all parabolas. If you looked at their graphs too, they'd all have the same shape graph. They'd all be like upward opening parabolas. They'd just be like shifted upward and downward depending on what that constant is. And so section 6.1 is really just about starting to recognize how to run this process backwards. I think a good analogy, if you think back to just like taking pre-algebra or even college algebra, squaring numbers is really easy. So you're like, all right, 2 squared is 4, 5 squared is 25. You can sort of figure out what all the squares are. But trying to do square roots, it's a lot harder. You need to have a really strong background in squaring numbers before square roots will be easy. And that's sort of the same thing in this chapter. Antiderivatives are easier if you have a solid understanding of how to take derivatives. And some of what you're going to be doing is just remembering back about where these things came from, right? So for example, remembering that the derivative of ln x is 1 over x. You have to remember that because if you need to find the antiderivative of 1 over x, there's no real process other than just to know where that came from originally. So I just want to pause here and see if there's any questions just about like basic antiderivatives. These would be things like powers of x, e to the x, 1 over x, square roots, cube roots, anything like that from section 6.1. I'm also drinking my coffee. Okay, hearing none, I'm gonna keep going. At the end, if we wanna take a look at some of the WebAssign problems, I'd be happy to do one, or maybe a problem that resembles one of the WebAssign problems. So let's do some basic antiderivatives and talk also about the notation. So what you've probably been seeing in assignments are things like this, right? That's a calculus symbol. It's called an integrand, and it's going to mean a couple different things in this chapter, but you'll see that it's not arbitrary that we use a single symbol for more than one thing. This is also sometimes called an indefinite integral. Basically means take the antiderivative of what comes next. So if we recognize that there's some derivative here, we have this little differential dx. The antiderivative of f prime is f of x plus c. I just want to sort of explain these different parts. So right now, that integral symbol really just means take an antiderivative. We're thinking of it as an instruction. Just like we had d dx, right, as an operator saying take the derivative, this tells us to take the antiderivative, right? So this is what we're going to take the antiderivative, so of this. And then the last part, and it's a little bit of a subtle point, but it's important. This dx, this differential, tells us with respect to which variable we're taking an antiderivative. So this says, all right, we're taking antiderivatives in terms of x. And just to show you why that's important, like if we had an indefinite integral of 5 dx, so the antiderivative of 5 with respect to x is 5x plus c. The antiderivative of 5 dt, right, that's sort of telling us what our independent variable is. The antiderivative of 5 dt would be 5t plus c. So for now, we can think of that differential as just telling us what our variable is when we're dealing with derivatives and antiderivatives. Okay, so this is in general what we're going to be doing. I'm going to just do a few examples here. This should resemble some of the problems from 6.1, and then we'll do some 6.2 ones as well. So for example, I think we just did this. Antiderivative of 2x with respect to x is x squared plus c. Now the nice thing about all of these antiderivative problems, even if they're a little bit tricky at first, you can always check your answer by taking your answer and differentiating, right? So d dx of x squared plus c, that's an easy derivative. Well, derivative of x squared is 2x, and the derivative of c is 0. That matches what we started with, so we just checked our answer. And I think especially in section 6.2, where you're starting to do these substitutions, they're a little bit tricky to recognize. It's definitely worth taking the time to check your answers on at least some of the problems as you move through it. So let's do a few more here. Put this up here. So let's take the antiderivative of, let's see, how about this? So x to the 4th power dx. All right, so this is a very common form to see for antiderivatives, just the power of x. And so what we have to do is we have to imagine the derivative process backwards. So when we took the derivative of x to some power, the power came out in front. So we multiplied by the power, and then we decreased the power by 1. So to reverse that process, we're going to do two things. We're going to increase the power by 1, right? So we're saying a derivative involving x to the 4th came from a function x to the 5th. Now, if this was my answer and I differentiated, I'd end up with 5x to the 4th, and that's not what I want here. I don't want 5x to the 4th. I want 1x to the 4th. So the way to fix that is to then multiply by the reciprocal of that power. Okay, and so we can check this again by just taking a derivative. So d dx of 1/5 x to the 5th plus c. Okay, so the power would come out in front, so we'd have 5 times 1/5 times x to the 4th power, and then c would go to 0. And 5 times 1/5 is just 1, and so we end up with our original function x to the 4th there. Okay, so this is a pretty common problem. We could make a formula. I'll write a formula here if you want. I think this is also in the book. It just sort of captures that pattern for powers of x. And this also goes for like square roots and cube roots and fractional powers and negative powers. So if we need to take the antiderivative of some power of x, so x to the nth power, well, okay, we'll do that same process. We'll increase the power by 1. So the power is now n plus 1. And we're going to multiply by the reciprocal of that number. Or equivalently, we're going to divide by that number. So if that number is 6, we divide by 6. If that number is 10, divide by 10. If that number is like 3/2, we can think of it as multiplying by the reciprocal. The reciprocal of 3/2 is 2/3. And then this plus c is very important. You will lose some credit if you're doing an antiderivative and you don't include that plus c. It's a really important conceptual idea that when we take an antiderivative, we get a whole family of functions. So 6.1, pretty much all the problems are what I call basic antiderivatives. It doesn't mean that they're easy, but it means that they come from a known function. They come from functions that we've differentiated previously in the course, and without fancy derivative rules like product quotient and chain rule. Section 6.2 has to do with antiderivatives that are in a very specific form, and here's the form that they're in. Section 6.2, every single problem can be written in this way. The antiderivative of some function u, right? So u times u prime, right? That's what we're looking for in section 6.2. So we're going to rewrite a bunch of the antiderivatives that I've given us, or that they've given us, in terms of some new function that's going to put it into a simpler form. So here's a quick example. I don't know it's an easy example, but it'll show the structure. If we had the antiderivative of e to the x squared times 2x dx. Okay, now that's not just a known derivative. That's not like a really common function like a power of x that we've differentiated a whole bunch of times. There's a lot going on. We have e to the x squared. We have this 2x out here. These things are multiplied, so it might not be clear like where this came from. 6.2 introduces this technique, sometimes called U substitution, that allows us to take a complicated looking antiderivative and turn it into a simple one. And so here's the key. What we're going to do is we're going to look inside the what we've been given, and what we're looking for is a function and its derivative, or maybe a function and something very close to its derivative. So what I notice in this problem is that there's an x squared as part of the problem, and there's also a 2x. And I know that 2x is the derivative of x squared. So one thing that I could do, and when I do this, it really is, there's a little bit of guess and check involved. I'm seeing if the problem gets easier if I make a substitution. So what I'm doing is I'm going to define some new function. We usually use u. There's no particular reason why, but sometimes called u substitution. I'm going to try letting u equal x squared. All right, so if I've identified a function and something that looks like its derivative, I'm going to let u equal that function. I should also say there are problems where there's more than one choice of u that will make the problem simpler. So you might do this a little bit differently for a given problem than you see in a video. You should still get the same answer. So if u equals x squared, then the derivative of u, and I'm going to write that using a differential. So du, we can understand as the derivative of u. Du equals 2x dx. Okay, so it's like when I did implicit differentiation. We're not making any assumptions about these derivatives here and how they're related. But if u equals x squared, then du equals 2x dx. This part came from my choice of u. If you picked a different thing for u, you'd get a different du. Now what we're hoping we can do is in the original problem, rewrite it strictly in terms of u. And so if I look at what I have here, my original integral, if I rewrite it in terms of u, well, u is x squared, so e to the x squared could be rewritten as e to the u. And 2x dx, well, that's 2x dx. That's right there. I have 2x dx, and 2x dx is equal to du. Okay, and if we look at how I've rewritten the integral, this is a much easier antiderivative, right? It's just e to the power of u, so its antiderivative would be e to the u plus c. Okay, so this is the goal. We accomplished it by our choice of u. Now, one of the things I don't love in WebAssign, on the 6.2 homework, they give you a couple problems where they say, hey, use this for u. But there's only like 1 or 2 problems like that. The whole key to the problem is this choice. If you make the right choice, the antiderivative becomes very easy. If you don't make the right choice, it's not going to help you. So the skill that you're developing in this section is basically through trial and error and through experience and just trying a bunch of problems, developing this ability to see what choice of u is going to work. And it comes back to identifying a function and its derivative. So let me finish this problem and we'll look at a couple more complicated examples, and then I'll stop and see if there's any more questions. So antiderivative of e to the u would be e to the u plus c, right? And then because this u is something that I invented along the way, when I write my final answer, I'm going to put it back in terms of x. So e to the u would just be e to the x squared plus c. And as a quick check, d dx of e to the x squared plus c, well, by the chain rule, we'd have e to the x squared times the derivative of that power, so times 2x, and then plus 0. And sure enough, e to the x squared times 2x, that's exactly what we started with in the problem here. Feel free to interrupt at any time. I'm going to go on and do a couple more problems. All right, if I erase. All right, I'll post the video too. If I do something too quickly, remember there'll be video of this so you can go back and pause or run slower or faster, depending on how you'd like to do it. Okay, so another example of u substitution. So suppose we had the following. We'll take the antiderivative of x times, let's say, x squared plus 1 to the 5th power dx. Sorry, the marker is not super clear. It's x squared to the first, or x squared plus 1 to the 5th power dx. So the very first thing is just to look at that and be like, okay, that's not a derivative of a function that I just know off the top of my head. That's not a 6.1 problem, it's a 6.2 problem. And so my job is to figure out if I can identify a good choice for u. So we're looking for u, and we're also looking for u prime, the derivative of u. And what I notice is I have x squareds here, and I have x to the 1st power here. So that makes me wonder, maybe could u be x squared? I'm going to write that as a question mark. Well, could u possibly be x squared plus 1, right? The derivative of x squared plus 1 is 2x. The derivative of x squared is 2x. Now, I really want to find not only u in the problem, but I want to find u prime. If I let u equal x squared plus 1, I'm just going to try that. You have to be willing to try. It's okay if you get some of these wrong. You're not going to waste too much time. You'll know immediately whether this helped or not. If we let u equal x squared plus 1, well, then the derivative of u would be, okay, the derivative of x squared is 2x dx plus 0. All right, so this is what I'm trying. I'm trying this. I don't know if it's going to work. Now I look back in the problem and say, all right, did that help? What would my new integral be? Well, there's u, so I would have u to the 5th, but I only have an x dx, and I want a 2x dx. Now there are a couple ways that we can deal with this. I'm going to show you my favorite way. The videos are a little bit different. They might show you a different technique, but when we almost have what we want, but we don't quite have it, we have an x dx and we want a 2x dx. Here's a way that we can hack the original problem to give us exactly what we need. We know that there's a constant multiple rule for derivatives, and there's also a constant multiple rule for integrals. And what that means is if I multiply my integral by 2 on the inside and 1/2 on the outside, I haven't really done anything. I haven't changed the integral. I've changed its form, but we know that if we multiply by 1/2 and we multiply by 2, those things will cancel each other out. So why would I do that? Well, the reason I did that is now I actually do have exactly what I need inside the integral. I do have a 2x dx, and that's exactly what I needed to substitute for du. Okay? So it's a cool way of modifying it. You're like, oh, I wish I had 2x dx. I only have 1x dx. So multiply by 2, multiply by 1/2, and suddenly we have the thing that we need. And our integral will be equal to the original problem. All right, so if I do that, then what I have is 1/2 times the integral. Now I'm going to switch it over to u's. So u is x squared plus 1. There's my u. So I'd have u to the 5th power. And now I've created this 2x dx, so that's my du. And before we even take the antiderivative, just notice how much nicer this integral is than that one, right? This is one of our basic antiderivatives now. We can do powers of x and powers of u very easily. So let me finish the problem now. We still have 1/2. To take the antiderivative of u to the 5th, we'd increase its power to 6. So we'd have u to the 6th power times 1/6, right? So if we took that derivative, 6 would come out, cancel, and we'd have u to the 5th plus c. Okay, and so our final answer, 1/2 times 1/6 is 1/12, u to the 6th. Now, remember what the c represents? The c represents any constant. So if we take any constant and we multiply by 1/2, we still get any constant. So there's no real reason to write 1/2 c here. We'll just write plus c to indicate that we could have any number at the end here and we'd get the same result. So last step now, I created u to help me in the problem, but the original problem was in terms of x. So I will rewrite our answer with x's instead of u's. So u was x squared plus 1. And that would be to the 6th power plus c. All right, so again, I want to pause, answer any questions. I think especially about this type of move here, this is a really powerful one, but can be also confusing for folks. Any questions about how or why I'm allowed to do that, or why I'd want to? Just so you guys know, also, there's text chat over on the right-hand side, or if you click chat at the bottom, you can do direct chat to other people in the meeting. You can share files. I've had some students who've done the collaborative quizzes, I think, using Zoom. So you can share a file. There's a built-in whiteboard function too, if you have a tablet or way of inputting data. I don't have an easy way of doing that. That's why I have this actual whiteboard here. Okay, so let's see, let me do maybe one more involving a natural log problem. Those can be a little bit tricky. Okay. So let's say we have to take the antiderivative of okay, so another sort of complex looking problem here. A couple comments on this. Just like the other sections of calculus or the other parts of calculus, sometimes doing some simplification before you do the problem is helpful. We can always do algebra first, calculus second. So for this particular problem, one thing I noticed is that in the numerator, both terms share a factor of x, and in the denominator, both terms share a factor of x. So before I do any calc, I could divide the numerator and the denominator by x, and then I'd have 6x plus 4 in the numerator, and x squared plus x in the denominator, I think, right? Yeah. I'll make sure this is going to turn out how I want it to. 3. Yeah. I'm actually going to change this problem very slightly to make it a little bit more convenient for this example here. Let's make it, let's see here. Let's make it 6x squared plus 3x. Yeah. Okay. So I did a little bit of algebra here. Sorry, bear with me on that. I think this will just make it a little bit quicker of an example. We don't have to do as much algebra on it. So that makes our problem a little bit simpler. It just reduces the powers. One thing we should recognize here, though, It's like we have a function divided by another function. Let me tell you what it's not going to be. It's not going to be the antiderivative of the top divided by the antiderivative of the bottom. We know not to fall for a trick like that because we know that there's things like the quotient rule. If we were to take the derivative of a quotient, we'd need low d high minus high d low all over rho squared. And that would be a little bit of a mess. It'd be hard to recognize like a quotient rule answer within an integral here. 6.2, what we're trying to do is recognize a chain rule problem inside our integral. So I'm looking for a function and its derivative. That's the search here. And what I notice is the denominator is now a degree 2 polynomial, and the numerator is a degree 1 polynomial. So my first thought is that maybe that denominator would be u, just because it's the higher powers of x. And especially because term by term, the numerator is 1 degree lower in both of these terms here. So let's see where that leads us. So let's try u equals x squared plus x. Well, if u equals x squared plus x, then du would be 2x plus 1 times dx. Okay, so I've chosen u, I'm seeing if it works, I find du, and then I zoom out for a minute, look back at my problem and say, does that help or does it hurt? Well, I'd have u in the denominator, and then the numerator I have 6x plus 3 times dx. So 6x plus 3 times dx. And down here I have 2x plus 1 dx, and they don't exactly match, right? So the previous problem, the way that I fixed this was by multiplying by a number and its reciprocal inside our integral. I'm going to fix this problem by actually working with my differential here, this du equals 2x plus 1 dx. Because if I take the second equation here and I multiply both sides by 3, look what I get. 3 du equals 3 times 2x plus 1. Well, 3 times 2x is 6x, and 3 times 1 is 1. So, sorry, 3 times 1 is 3, obviously. All right, so by multiplying both sides by 3, look what I get. I actually get exactly what I have inside my integral here, right? So this is like this step, like if you don't have exactly u and u prime, or like u and du inside your function here, you kind of have to hack it. You either have to hack your result here or hack your original integral to get it into a form where you can do a substitution. Okay, so then my integral rewritten in terms of u, well, okay, so 6x plus 3 dx, 6x plus 3 dx, that's equal to 3 du. So 3 du over u. Or more commonly, we just see this written like this, 3 over u du. Oops, I ran out of space there. Okay, so now this is a much simpler antiderivative to take. Remember that the derivative of 1 over u, right, that'd be u to the negative first power. The derivative would be u to the negative second power. But the antiderivative of 1 over u is natural log. And another important detail here, when we take an antiderivative involving natural logs, we know that we can't take natural log of 0 or of a negative number. So one thing that we'll do here is we'll take the natural log and we'll just put some absolute value bars around u to make sure that it's positive. Okay, so we have 3 times the antiderivative of 1 over u du. So 3 times natural log u plus c. And finally, and again, if this is a quiz or exam, if you leave it in terms of u, you'll probably get 3 points out of 4. If you forget your plus c, you'll probably get 3 points out of 4. So just make sure after you've done all this hard work that you write the final answer in terms of x and you include that constant. So my choice of u was x squared plus x, so 3 times the natural log of x squared plus x plus c. And this is a problem, I don't think I'll do this with you guys right now, but if I were doing this on a WebAssign problem or on a quiz, this is complex of a problem enough that I would definitely take this answer and differentiate to make sure that I end up with what I started with. So that's kind of like what I wanted to do, is just offer like a little bit more conversational tone on what's going on in these two sections overall. I hope that's a little bit helpful. Do you guys have any questions or problems that you'd like to look at? I'm not hearing a whole lot. So yeah, guys, I appreciate you tuning in.